Look at your hand right now. I mean it. Whatever you are doing, just pause for a second and really look at it. Look at the color. Whether it is pale ivory, golden tan, warm brown, or deep ebony, that color is not random. That color is a message. It is a letter written by your ancestors thousands and thousands of years ago, sealed in your DNA and delivered to you across hundreds of generations. It is telling you where they lived, what they endured, and how they fought to survive in places that tried everything they could to kill them. And here is something that might genuinely surprise you. If you happen to have light skin, what people commonly call white skin, you are looking at one of the newest developments in the entire history of our species. Not ancient, not primordial, new, staggeringly new. We are talking about a change that is more recent than the invention of agriculture, more recent than the first cities, more recent than the earliest pottery. On the grand timeline of human existence, pale skin basically showed up yesterday. It is the biological equivalent of wet paint. Every single human being alive today, all 8 billion of us, every person on every continent, in every country, speaking every language, had ancestors who lived in Africa roughly 200,000 years ago. And every single one of those ancestors had dark skin, rich, deep, melanin-heavy skin that was built from the ground up for one purpose: surviving the relentless equatorial sun. That was the original. That was the default. That was what a human being looked like for the vast majority of the time our species has existed. So how did some of us end up looking so wildly different from one another? How is it that a person from Stockholm and a person from Lagos can look at each other and see such dramatically different appearances when they are the same species, when they share the same fundamental biology, when their ancestors were once the same people living in the same place under the same sun? The answer to that question is not what most people expect. It is not about different races evolving separately over millions of years. It is not about deep, fundamental, biological divisions between groups of people. The real answer is far more fascinating than any of that. It is a story about desperate survival in hostile new environments. It is about the human body's breathtaking ability to reshape itself when the alternative is extinction. It is about random mutations, tiny accidents in the copying of DNA, that gave certain individuals an edge so powerful that within just a few thousand years, entire populations were transformed beyond recognition. And the science behind all of it turns out to be more complex and more beautiful than anyone imagined until very recently. This is not a simple story about one gene switching on or off. It is about multiple genetic mutations happening in different populations at different times and in different places, all of them trying to solve the same problem, but doing it in slightly different ways. It is about a delicate balance between two essential nutrients, vitamin D and folate, and the catastrophic consequences of getting that balance wrong. It is about rickets and birth defects and infant mortality. It is about mothers in the brutal cold of prehistoric winters doing everything in their power to keep their children alive, and about a sun that was no longer strong enough to do its part. And the beauty of this story is that it unfolds slowly. Evolution is never in a rush. We are going to travel through roughly 50,000 years of human history, step by step, generation by generation, following our ancestors as they spread across the face of the earth, and watching as their bodies slowly changed in response to the sunlight conditions of their new homes. We are going to meet the specific people, or at least the specific genetic accidents, that made pale skin possible. We are going to discover why some populations became light while others did not, even when they lived at similar latitudes. We are going to uncover the surprising and unexpected role that farming played in accelerating these changes, pushing evolution into overdrive at a speed that almost defies belief. And along the way, we are going to confront what skin color actually means in biological terms, and perhaps more importantly, what it does not mean. Because modern genetics has proven something beyond any reasonable doubt. The physical differences that we can see between different human populations, the differences that we have used to build entire systems of classification and discrimination and hierarchy, represent the absolute tiniest sliver of our genetic code. We are talking about a handful of genes out of roughly 20,000. The overwhelming majority of human genetic diversity exists within populations, not between them. Two people from the same village in Nigeria can be more genetically different from each other than either of them is from a person in Finland. Skin color is a surface-level adaptation, literally surface level, and it tells you almost nothing about what is happening beneath. But tonight we are not here for politics or sociology. We are here for the story itself, the actual scientific, archaeological, genetic story of how humans became white. It is a detective story written in ancient DNA, pieced together by scientists over decades of painstaking research, and it is far more interesting and far more surprising than any simplified version you might have heard before. So settle in, get comfortable, let the tension drain out of your shoulders, let your breathing slow. We are about to travel back to a time when every human on Earth was dark, and we are going to follow the long, winding, improbable journey that led some of them to become something entirely different. A journey of survival, adaptation, and the almost unbelievable flexibility of the human body. The mystery written in your skin is about to unfold. Let us begin at the very beginning, because before anyone was white, before anyone was pale, before skin color became something that human beings even had reason to think about, we were all dark. Every single one of us. Your ancestors. My ancestors. The ancestors of every person you have ever met. All of them, without exception. Around 300,000 years ago, in the sun-scorched landscapes of Africa, modern humans first appeared, and they all shared one unmistakable trait: dark brown skin, dense with melanin, exquisitely tuned to the environment that had created them. This was not an accident. Evolution does not deal in accidents when survival is at stake. Dark skin was the answer to a very specific and very deadly problem, and that problem was the African sun. Try to picture the world your earliest ancestors lived in. Not the Africa you might see in a documentary today, though parts of it remain similar, but the Africa of the Middle Pleistocene. Immense grasslands stretching to the horizon in every direction, interrupted here and there by the gnarled silhouettes of acacia trees and jagged outcroppings of ancient rock. The equatorial sun hammering down with an intensity that is genuinely difficult to comprehend if you have never stood beneath it. At midday, there is virtually no shade. The sun hangs directly overhead, and ultraviolet radiation pours down like an invisible fire, relentless and inescapable. This is where human beings evolved, not in dense forests where thick canopies of leaves filter the sunlight into dappled green patterns, not in temperate zones where clouds regularly roll in to provide relief. Humans evolved in the wide, open savannas of equatorial Africa, where our ancestors had long since abandoned the trees and were learning the strange new art of walking upright across vast, exposed grasslands. And that upright posture changed everything. When our earlier ape ancestors moved on all fours, the geometry of their bodies provided a kind of natural shelter. Most of their skin was shaded by their own torso. The sun struck mainly their backs, and thick body hair offered an additional layer of defense. But when our ancestors stood up, when they began walking on two legs and gradually lost most of their body hair, probably as an adaptation to improve cooling efficiency through sweating, they suddenly exposed enormous areas of bare skin directly to the sun. The tops of their heads, their shoulders, their chests, their arms, their faces, all of it now fully vulnerable to the ultraviolet onslaught. This created a genuine biological crisis. Ultraviolet radiation is not merely uncomfortable. It is destructive at the molecular level. It breaks chemical bonds. It damages DNA. And most critically for our ancestors, it destroys folate. Folate is a B vitamin, and its importance to human survival cannot be overstated. It plays a central role in protecting DNA during cell division, especially the rapid, frenetic cell division that occurs when embryos are forming in the womb. Without adequate folate, neural tubes do not close properly. Spines develop incorrectly. Brains do not form as they should. Pregnancies fail, often catastrophically. Even in adults who are not pregnant, folate deficiency causes anemia, chronic weakness, and a sharply reduced ability to heal wounds. In the harsh and unforgiving environment of prehistoric Africa, where every wound could become infected and every moment of weakness made you vulnerable to predators, folate deficiency was effectively a death sentence. And here's the terrifying part. The African sun destroys folate with ruthless efficiency. Scientific studies have demonstrated that just a few hours of intense UV exposure can degrade folate levels in the bloodstream by more than half. Now think about what daily life was like for your earliest ancestors. They did not live in buildings. They did not wear woven clothing. They did not drive to air-conditioned offices. They spent virtually every daylight hour outside, walking, hunting, gathering, hauling water, tending to children, all of it under direct and unrelenting sunlight. Without some form of protection, their folate reserves would have been under constant assault, depleted faster than their bodies could replenish them. This is where melanin enters the story. Melanin is one of the most elegant solutions nature has ever devised. It is a pigment produced by specialized cells called melanocytes, which reside in the deepest layer of the skin, the stratum bile. Melanin comes in several forms, but the one that matters most for UV protection is eumelanin, the brown-black pigment that gives skin its deeper, richer tones. Eumelanin works like billions of microscopic umbrellas distributed throughout the layers of your skin. Each molecule absorbs ultraviolet photons and converts their energy into harmless heat, dissipating it before it can penetrate to the deeper layers where blood vessels carry folate-rich blood and where DNA-containing cells are most actively dividing. The more melanin you have, the more of these tiny shields are deployed, and the more effectively your skin blocks incoming UV radiation. The numbers are striking. Deeply pigmented skin, the kind that characterized all early modern humans, can absorb and neutralize ultraviolet radiation dozens of times more effectively than lightly pigmented skin. It is not a perfect shield. No biological adaptation ever is. Some UV radiation still gets through. But the protection is remarkable, effective enough that a person with dark brown skin can spend an entire day under the equatorial sun without suffering significant folate depletion. This was not merely a nice advantage. In the environment where human beings first evolved, this was an absolute biological requirement. Women with insufficient melanin would have experienced dramatically higher rates of pregnancy failure, birth defects, and infant mortality. Their children would have been more vulnerable to sunburn, skin damage, and the long-term cumulative effects of chronic UV exposure. Adults without adequate melanin protection would have suffered ongoing folate deficiency and the cascade of health problems it triggers, from anemia to impaired wound healing to weakened immunity. Natural selection does not take a gentle approach to problems this fundamental. When a trait is directly tied to reproductive success and child survival, the evolutionary pressure is overwhelming. Any random genetic variation that happened to increase melanin production would have been powerfully favored. Individuals carrying such variations would have been healthier, would have had more successful pregnancies, would have raised more children to adulthood, and those children would have inherited the same melanin-boosting genes. The result was swift, at least in evolutionary terms. Within just a few thousand generations, which sounds like a lot, but is actually a blink of an eye on the timescale of life on Earth, every human being living in equatorial Africa had dark skin. Not most of them, not the majority, every single one. The genetic evidence for this is unambiguous. When scientists examine the oldest branches of the human family tree, the populations that have remained in Africa throughout the entire history of our species, they find that the ancestral state of skin color genes is uniformly dark. The mutations that would later produce lighter skin in other parts of the world simply did not exist yet. Or if they appeared as random flukes, as all mutations initially do, they were ruthlessly selected against. In equatorial Africa, a mutation that reduced melanin production was not a neutral variation or an interesting novelty. It was a threat to survival. It would have made its carrier more vulnerable to folate depletion, more susceptible to sun damage, less likely to reproduce successfully. Natural selection would have erased such mutations from the population almost as quickly as they appeared. Think for a moment about what this means for the first 240,000 years, perhaps even longer, of modern human existence. Skin color was not variable. It was not something that differed between groups or between individuals in any dramatic way. Every human who looked at another human saw someone whose skin was approximately the same deep brown shade as their own. There were no categories based on color, no hierarchies, no distinctions. Dark skin was not a trait that required explanation or classification. It was simply what human beings looked like. It was as unremarkable and universal as having 2 eyes or 10 fingers. Life in those early African populations was challenging, certainly, but it was not a constant struggle against a hostile environment. Quite the opposite. Your ancestors were superbly adapted to their world. They could hunt during the blistering heat of midday without suffering debilitating sun damage. They could gather plant foods in exposed clearings and open grasslands without worrying that the ultraviolet radiation was silently destroying essential nutrients inside their bodies. Women could carry pregnancies to term and deliver healthy children whose nervous systems had developed properly because their mothers had maintained adequate folate levels throughout gestation. The archaeological record from this period paints a picture of humans not just surviving, but genuinely thriving. They were creating increasingly sophisticated stone tools, developing specialized hunting techniques, exploiting diverse food resources. They were building complex social networks, cooperating in ways that allowed them to take down prey much larger than themselves, sharing food, caring for the sick and injured. By at least 100,000 years ago, and probably considerably earlier, they were producing art, decorating objects with pigments, creating beads from shells, engraving patterns into bone and stone. Through all of this technological and cultural flowering, through all these millennia of innovation and social development, their skin remained what it had always been, consistently, uniformly dark. Because in Africa, beneath that fierce equatorial sun, dark skin was simply what worked. It was the right solution to the right problem, and there was no reason for it to change. But skin color, like so many things in biology, is not about solving just one problem. It is a balancing act, a compromise between competing biological needs. Because while ultraviolet radiation is genuinely dangerous, capable of destroying folate and damaging DNA, it is also genuinely essential. Humans require sunlight to produce vitamin D, a hormone that is critical for bone development, immune function, muscle contraction, and dozens of other physiological processes that keep the body running. The mechanism is elegantly simple. When UVB radiation strikes the skin, it triggers a chemical reaction in the cells that converts a cholesterol precursor into vitamin D3, which is then processed by the liver and kidneys into its active hormonal form. Without this reaction, the body cannot adequately absorb calcium from food, and without calcium, bones cannot mineralize. They remain soft, weak, and deformable. The immune system cannot mount proper responses to infection. Muscles cannot contract efficiently. The consequences are severe and wide-ranging. In equatorial Africa, this was never a problem. The sun was so intense, so reliably powerful year after year, that even skin heavily loaded with melanin could produce more than enough vitamin D. The sheer volume of UV radiation was so great that even after melanin blocked 90% of it, the remaining 10% was still sufficient to drive adequate vitamin D synthesis. Your dark-skinned ancestors got all the vitamin D they needed despite their natural sunscreen being turned up to maximum strength. The equatorial sun was powerful enough to punch through even nature's best defenses. This is the crucial insight. In the environment where humans originally evolved, dark skin represented the perfect balance. It provided maximum protection against the dangers of excessive UV exposure, safeguarding folate, protecting DNA, preventing sun damage, while still allowing enough UV radiation through to maintain healthy vitamin D production. It was the Goldilocks solution. Not too much UV penetration, not too little. Just exactly right. Your earliest ancestors had no idea any of this was happening, of course. They did not know about melanin or ultraviolet radiation or the biochemistry of vitamin D synthesis. They did not understand why their skin was the color it was or what purpose that color served. They simply lived their lives under the African sun, generation after generation, century after century, millennium after millennium, shaped by invisible forces they could neither see nor comprehend. But those forces were real, and they were immensely powerful. They wrote the opening chapter of the human story in dark brown pigment, and that chapter remained unchanged for longer than civilization has existed. Then, around 60 to 70,000 years ago, some of those dark-skinned Africans did something that no human had ever done before. They left. Small groups, probably numbering no more than a few hundred individuals at first, began moving out of Africa. They crossed from the Horn of Africa into the Arabian Peninsula, or perhaps through the Sinai into the Levant, or possibly both. They carried with them everything that had made them successful in Africa: their tools, their knowledge, their social structures. their languages, their dark skin. They did not know it, but they were carrying an adaptation that was perfectly calibrated for the environment they were leaving and increasingly dangerous for the environments they were about to enter. The story of how human skin color diversified, how some populations lightened while others remained dark, begins with this migration. It begins with dark-skinned people walking into places where that very darkness, the trait that had protected their ancestors for hundreds of thousands of years, would slowly become a threat to their survival. But before we follow them into those new and challenging environments, let us sit for a moment with what we have established. The deepest, oldest, most fundamental adaptation in human history, the one that all of us carried for longer than any other, was dark skin. Rich, melanin-dense, sun-adapted, beautifully functional dark brown skin. Before we were diverse, before we were scattered across the globe, before we developed the superficial physical differences that we have spent so much of our history fighting about, we were all the same. All children of the African sun, all wearing the same biological armor, all painted in the same ancient shades. That darkness is not a variation or a deviation from some imagined norm. It is the original human condition, the baseline from which every other skin color eventually emerged. And in its own quiet way, that truth is extraordinary. Every human being alive today, regardless of what they look like now, descends from people who looked essentially the same. We all start from the same place, shaped by the same sun, protected by the same molecular shields that our most distant ancestors evolved beneath the oldest skies on Earth. Now, the migration. Let us talk about why it happened, because the decision to leave Africa, or rather the slow, multi-generational drift out of Africa, is one of the most consequential events in the history of life on this planet. And the reasons behind it are more complicated and more interesting than a simple desire to explore. Your ancestors had survived the bottleneck. They had endured a period when the total human population may have crashed to as few as a few thousand individuals, a brush with extinction so close that it left permanent scars in our DNA. You can still see the evidence today in the remarkably low genetic diversity of the human species compared to other great apes. We came terrifyingly close to disappearing entirely, and then we bounced back. After the bottleneck, populations recovered and expanded. Humans spread across Africa, adapting to a stunning variety of environments within the continent, from dense tropical forests to arid deserts, from coastal regions to mountain highlands. They developed new tools, new hunting strategies, new ways of organizing their societies. For hundreds of thousands of years, they thrived in the continent that had given birth to their species. Then, somewhere between 70,000 and 100,000 years ago, some of them began to leave. Not all of them, not even most of them, just small groups, moving out of familiar territory and into the complete unknown. Why would anyone do this? Why abandon Africa, where humans had lived successfully for millions of years, where the climate was familiar, where people knew which plants were safe to eat and which would kill them, where they understood the behavior of the animals they hunted, where they had social networks and established territories and all the accumulated knowledge of countless generations? The honest answer is that we do not know with certainty. The archaeological record from this period is fragmentary, and the people involved left no written accounts of their motivations. But we can make educated inferences based on what we know about human behavior, environmental conditions, and the patterns we see in the evidence. The first factor was almost certainly climate. Africa's climate has never been static. It cycles between wetter and drier periods, driven by changes in Earth's orbital parameters and ocean circulation patterns. During wet periods, the Sahara, which we think of today as a vast and impassable desert, would transform. It would green up, becoming a grassland savanna dotted with lakes and crisscrossed by rivers. Animals would spread northward to exploit these new pastures, and human populations would follow them. Then, when the climate shifted back toward aridity, the Sahara would dry out again. The lakes would shrink and disappear. The grasslands would wither, and the human populations that had expanded northward would be forced to contract, retreating southward toward more reliable water sources. But not everyone would make it back. Some groups would become stranded along the margins, cut off from their original territories by expanding desert. Some would discover that instead of retreating south, they could keep moving north or east, out of Africa entirely, into the Middle East and beyond. This Saharan pump hypothesis, as scientists call it, suggests that the initial movements out of Africa were not bold expeditions into the unknown, but rather the natural result of populations following favorable conditions and then getting pushed onward when those conditions changed. People did not set out to discover new continents. They simply followed the water and the game, and the water and the game led them out of Africa. The second factor was population pressure. By 70,000 years ago, Africa probably held hundreds of thousands of people, possibly more. That might not sound like many compared to today's billions, but for hunter-gatherer societies, which require vast territories to support relatively small groups, it was becoming crowded. The best hunting grounds were already claimed. The most productive gathering areas were already occupied. Competition between groups was intensifying. In every generation, some individuals and some groups would have felt the squeeze more acutely than others. Young men looking to establish their own territories and attract mates. Smaller groups pushed to the margins by larger, more powerful neighbors. Families caught between competing claims. For these people, the unknown lands beyond Africa's borders might have seemed less threatening than the known conflicts at home. Moving into new territory, even unfamiliar territory, at least offered the possibility of space, of resources, of freedom from competition. The third factor was capability. By this point in their history, humans had become extraordinarily skilled at adapting to new environments. The descendants of the bottleneck survivors had spent hundreds of thousands of years honing their survival abilities. They could read landscapes, assess threats, identify potential food sources, develop new hunting strategies on the fly. They had sophisticated tools, complex communication, and flexible social structures that allowed them to cooperate in large groups. The unknown was still unknown, but it was less frightening to people who had proven, generation after generation, that they could handle whatever the world threw at them. And there is a fourth factor, one that is harder to quantify, but perhaps the most fundamentally human of all: curiosity. The simple, irrepressible desire to see what is over the next hill. Every human society that has ever been studied, without exception, contains individuals who are restless, who are drawn to exploration, who feel a deep pull toward the unfamiliar. This trait is not universal within populations. Not everyone feels it equally, but it appears in every population that has ever existed. Some people are simply wired to move, to discover, to push boundaries. And when those individuals started walking north and east out of Africa, they set in motion a chain of events that would transform the species forever. The migration itself was not dramatic in the way we might imagine. There was no single moment of departure, no decisive crossing of a border, no awareness among the participants that they were doing something historic. It was slow, incremental, and multi-generational. Groups moved a little farther each generation. Seasonal camps became semi-permanent settlements. Semi-permanent settlements became permanent homes. And from those new homes, the next generation pushed a little farther still. The first major exit route was probably through the Middle East, across the Sinai Peninsula, or along the coastline of the Red Sea. During the favorable climate periods that coincided with these early migrations, the Arabian Peninsula was not the harsh desert it is today. It was grassland, green and fertile, crossed by rivers and dotted with lakes. Archaeological sites from this period show human presence along these water sources, groups moving steadily along corridors of habitability, following the herds of large animals that grazed on the seasonal vegetation. Some groups chose the coast. They followed the shoreline of the Red Sea around the southern tip of the Arabian Peninsula and then eastward along the coast of the Indian Ocean. This coastal route had enormous advantages. The sea provided a virtually inexhaustible supply of food. Shellfish, fish, sea birds, marine mammals. All of these resources were available year-round, regardless of conditions inland. Coastal environments were also buffered against the extreme seasonal swings that made interior regions so challenging. When the interior dried out and game became scarce, the coast remained productive, and the shoreline itself served as a natural navigation tool, an unmistakable landmark that made it impossible to become truly lost. Just keep the water on one side and keep walking. These coastal migrants became specialists in a way of life that was entirely new to the human experience. They learned to read the tides. They figured out which shellfish were safe to eat and which were toxic. They developed techniques for catching fish in shallow water. They learned to harvest seaweed and other marine plants. Archaeological sites along ancient coastlines, many of which are now submerged beneath seas that rose as ice age glaciers melted, show evidence of sophisticated seafood processing. These were not desperate refugees scavenging whatever they could find. These were skilled, knowledgeable people developing new technologies and new food traditions. They were innovating in real time, creating an entirely new way of being human. Other groups turned inland. They followed the great river valleys that cut through the otherwise challenging terrain of the Middle East and Central Asia. The Tigris and Euphrates, the Indus, the rivers that drain the mountains of Central Asia, all of these became highways for human migration. River valleys were oases of fertility and landscapes that could otherwise be punishingly dry or impossibly rugged. They provided reliable water, which was the single most important resource for survival. They attracted game animals, which came to drink. They supported dense vegetation, which provided food, fuel, and building materials. And they offered natural routes through mountains and across deserts that would have been impassable otherwise. But here is where the story takes a fascinating turn. These migrants were not walking into an empty world. They were entering territories that were already occupied, not by other modern humans, but by their distant evolutionary cousins. The Neanderthals were there, spread across Europe and Western Asia, where they had lived successfully for hundreds of thousands of years. The Denisovans were there too, inhabiting a vast range from Siberia to Southeast Asia, a population we know almost entirely from DNA evidence and a handful of bone fragments found in a cave in the Altai Mountains. The Neanderthals in particular were formidable. They were stockier and more muscular than modern humans, built for the cold climates of Ice Age Europe. Their brains were at least as large as ours, possibly larger. They made sophisticated tools, hunted large and dangerous game, used fire, built shelters, and there is growing evidence that they practiced symbolic behavior, things like burying their dead, using pigments, perhaps even creating simple art. They had been the dominant hominin in Europe for 300,000 years by the time modern humans showed up, and they were not necessarily welcoming to newcomers. The archaeological record tells us that modern humans and Neanderthals coexisted in the same regions for thousands of years. In the Middle East, the overlap lasted for perhaps 30 to 50,000 years. In Europe, the coexistence was shorter but no less significant, lasting from roughly 45,000 to about 30,000 years ago. During this time, the two populations interacted in ways that left permanent marks on our species. We know with absolute certainty that they interbred. Every person alive today who has ancestry outside of sub-Saharan Africa carries Neanderthal DNA in their genome, typically between 1 and 4% of their total genetic code. This might not sound like much, but across the entire modern human population, a substantial portion of the Neanderthal genome survives, distributed in different fragments among different people. Some of those inherited genes turned out to be extraordinarily useful. Genes affecting immune function, genes influencing skin and hair characteristics, genes that helped modern humans adapt to the colder, darker environments of Europe and Asia. The Neanderthals had spent hundreds of thousands of years evolving in those environments, and when modern humans acquired some of their genetic adaptations through interbreeding, it provided a significant boost. The Denisovans left their mark as well. Modern populations in East Asia, Southeast Asia, Australia, and the Pacific Islands carry varying amounts of Denisovan DNA. In some cases, these inherited genes have been spectacularly valuable. Tibetan populations, for example, carry a Denisovan variant of a gene called EPS1 that helps them thrive at extreme high altitudes where the oxygen is thin. This single gene, acquired from an extinct species through ancient interbreeding, is the primary reason Tibetans can live comfortably at elevations that would incapacitate most other humans. Other Denisovan genes have been linked to immune function and metabolic adaptations in various Asian and Pacific populations. As modern humans continued their spread, they encountered an astonishing variety of environments, each presenting its own unique set of challenges. Groups moving north into Central Asia faced the steppe, a vast expanse of rolling grassland stretching from Eastern Europe to Mongolia. Life on the steppe was defined by extremes. Brutally cold winters, brief but intense summers, relentless wind, and a landscape so flat and featureless that navigation itself was a challenge. Survival depended on following the enormous herds of horses, bison, and mammoths that migrated across these plains with the seasons. The hunting was spectacular for those with the skills to exploit it, but the lifestyle demanded incredible endurance, mobility, and adaptability. Other groups moved east, into the forests and river valleys of what is now China and Southeast Asia. These regions were lush and productive, but presented completely different challenges. Dense forests full of unfamiliar plants and animals. River systems prone to catastrophic flooding during monsoon seasons. Tropical diseases caused by parasites and pathogens that had never existed in Africa. The groups that succeeded in these environments had to develop entirely new survival strategies, new tools, new knowledge systems, new ways of organizing their societies. Still others moved into Europe, entering the heartland of Neanderthal territory. The Ice Age European landscape was unlike anything their African ancestors could have imagined. Vast glaciers covered the northern portions of the continent, reaching as far south as modern-day Germany and Poland during the coldest periods. Below the ice line, the landscape was a patchwork of tundra, boreal forest, and grassland, teeming with large animals like woolly mammoths, woolly rhinoceroses, cave bears, giant deer, and herds of reindeer that numbered in the hundreds of thousands. The encounters between modern humans and Neanderthals in Europe seem to have been particularly significant. Archaeological evidence shows the two species living in close proximity in regions like the Levant and southern Europe for thousands of years. They used similar tools, hunted similar prey, and in some cases appeared to share cultural practices. But something about modern humans gave them an edge. Perhaps it was their slightly more sophisticated communication abilities, which allowed for more complex planning and coordination. Perhaps it was their more flexible social structures, which enabled larger groups to cooperate effectively. Perhaps it was their greater capacity for innovation, their tendency to rapidly develop new tools and techniques in response to changing conditions. Or perhaps it was simply a matter of numbers and timing, of being in the right place when climate shifts created opportunities and eliminated competitors. Whatever the reasons, the outcome is clear. Modern humans gradually expanded their range while Neanderthal populations contracted. By about 40,000 years ago, Neanderthals had vanished from most of their former territory, surviving only in scattered refuges along the margins of their range, in caves along the coast of Spain, in isolated valleys in the Balkans. By 30,000 years ago, they were gone entirely, the last members of a lineage that had endured for hundreds of thousands of years finally winking out of existence. The pace of the human diaspora was breathtaking when measured in evolutionary terms, but excruciatingly slow when measured in human lifetimes. It took thousands of years for modern humans to spread from Africa to Australia, a journey that required crossing open water for the first time in human history. Thousands more years to fully colonize Europe, pushing northward as glaciers retreated and then retreating southward when they advanced again. Many more thousands of years to reach the Americas, crossing the land bridge that connected Siberia to Alaska during the last ice age, or perhaps traveling along the Pacific coast by boat. No individual person traveled these immense distances. The migration was a relay race spanning hundreds of generations. Each generation moved a little farther, explored a little more territory, established new settlements that became the launching points for the next wave of exploration. A family might move 20 miles in a lifetime. Their grandchildren might move another 20. Over thousands of years, those incremental movements added up to a journey spanning continents and oceans. And with every step of this journey, with every new environment encountered and every new challenge overcome, natural selection was quietly at work. The humans who left Africa carried with them the dark skin that had served their species so well for hundreds of thousands of years. That skin, loaded with melanin, calibrated for the intense UV radiation of equatorial Africa, was perfect for the place they had left behind. But with each step northward, the sunlight grew weaker. The days grew shorter in winter and longer in summer, creating seasonal extremes that equatorial Africa never experienced. The sun hung lower in the sky, its rays traveling through more of the atmosphere before reaching the ground, filtering out more and more of the UVB radiation that dark skin needed to produce vitamin D. A crisis was building. slowly, invisibly, but with the inexorable force of physics and biology. The dark skin that had been humanity's greatest asset was becoming, in these new northern environments, a potentially fatal liability. The stage was being set for one of the most dramatic physical transformations in the history of any species, a transformation that would reshape the appearance of entire populations within just a few thousand years. But that transformation would have to wait. For now, dark-skinned humans were pushing into new territories, meeting new challenges, encountering new peoples, and remaking the world with every step. They did not know that their bodies were about to change. They did not know that the sun they were walking toward was too weak to sustain the skin they had been born with. They only knew what every migrating human has always known, that there was something over the next hill, and they needed to find out what it was. The journey continued. The crisis deepened, and the first genetic accidents that would eventually turn dark skin pale were still thousands of years in the future, waiting in the randomness of DNA replication for the moment when they would finally occur, and when the desperate pressure of survival in a sunlight-starved world would seize upon them and spread them through entire populations with a speed that still astonishes scientists today. But we will get to that. For now, the migrants are still walking, still dark, still carrying the ancient inheritance of the African sun into lands where that inheritance will be tested as never before. The world is vast and strange and full of wonders, and our ancestors are meeting it with nothing but their intelligence, their courage, and their endlessly adaptable bodies. The transformation is coming. But first, the crisis has to get worse. Much worse. So your ancestors made it north. They had crossed out of Africa, pushed through the Middle East, and fanned out across Europe and Central Asia. Generation after generation, they kept moving, kept adapting, kept finding ways to survive in landscapes that looked nothing like the sun-baked savannas where their species had been born. They built shelters against the wind. They wrapped themselves in animal hides against the cold. They learned which berries were safe and which animals could be ambushed at water crossings. They were brilliant, resourceful, endlessly creative in the face of the unknown. But they were carrying something with them that all their intelligence and all their ingenuity could not fix. Their skin. That beautiful, melanin-rich, dark brown skin that had been the crowning achievement of hundreds of thousands of years of equatorial evolution. The skin that had shielded their ancestors from the brutal African sun. The skin that had protected folate reserves, prevented DNA damage, allowed generation after generation of healthy pregnancies and healthy children. That skin was about to betray them. Here is the thing that nobody tells you about the great human migration, the part that gets left out of the triumphant narrative of exploration and discovery. Moving into new territory is not just about finding food and avoiding predators and figuring out how to stay warm. It is about your body suddenly existing in an environment it was never designed for. Every cell, every biochemical process, every finely tuned system that evolved over millions of years to function in one specific set of conditions is now operating in conditions that are fundamentally different. And when the mismatch is severe enough, when the gap between what your body expects and what the environment provides is wide enough, the consequences are not subtle. They are catastrophic. For dark-skinned humans moving into northern latitudes, the most critical challenge was not the cold. It was not the unfamiliar animals or the strange vegetation or the ice sheets grinding across the landscape. It was something far more insidious, something completely invisible. It was sunlight, or more precisely, the absence of it. Let me explain exactly what was happening, because the mechanics of this crisis matter. They are the engine that drove one of the most dramatic physical transformations in the history of our species, and understanding them is essential to understanding why humans look the way they do today. Vitamin D is not really a vitamin at all. That is a misnomer that stuck because of the historical circumstances of its discovery. Vitamin D is a hormone, a powerful signaling molecule that your body manufactures internally when ultraviolet B radiation from the sun strikes your skin. The process is elegant in its simplicity. UVB photons penetrate the outer layers of the skin and reach a cholesterol precursor molecule called 7-dehydrocholesterol that sits in the cell membranes of your skin cells. When a UVB photon hits this molecule, it breaks one of its chemical bonds, converting it into pre-vitamin D3. Body heat then gradually transforms pre-vitamin D3 into vitamin D3, which enters the bloodstream and travels to the liver, where it is converted into calcidiol, and then to the kidneys, where it is converted into calcitriol, the fully active hormonal form. This might sound like a lot of steps, and it is. But under the right conditions, the right being the conditions of equatorial Africa, where the process evolved, it happens smoothly and automatically. You walk around in the sun, your skin does its chemistry, and your body gets the vitamin D it needs. You do not have to think about it. You do not have to plan for it. It just happens as naturally and reliably as breathing. But the right conditions are critical. The entire process begins with UVB photons reaching the skin in sufficient quantities. And UVB radiation is extraordinarily sensitive to the angle at which sunlight strikes the Earth's surface. At the equator, the sun passes almost directly overhead. Its rays travel through the minimum possible amount of atmosphere before reaching the ground. UVB radiation is intense and abundant. Even heavily pigmented skin that blocks 90% or more of incoming UV radiation, still receives enough UVB penetration to drive robust vitamin D synthesis. Move to 45 degrees north latitude, roughly the latitude of Milan or Montreal or Vladivostok, and the picture changes dramatically. The sun never reaches directly overhead, not even at the summer solstice. Its rays strike the Earth's surface at an oblique angle, traveling through far more atmosphere. That extra atmosphere scatters and absorbs UVB radiation before it can reach the ground. Even on the brightest summer day, the UVB intensity at 45 degrees north is a fraction of what it is at the equator. And that is summer. In winter at the same latitude, the sun hangs so low in the sky that its rays travel through so much atmosphere that virtually no UVB radiation reaches the surface at all. For months at a time, from roughly October to March at these latitudes, vitamin D production in the skin effectively shuts down completely, regardless of how much time you spend outdoors, regardless of how much skin you expose. The physics simply do not allow it. Now move even farther north, to 55 degrees, the latitude of Moscow or Edinburgh or the southern tip of Alaska, to 60 degrees, the latitude of Stockholm or Helsinki or Anchorage. At these latitudes, the vitamin D winter stretches from September to April, 7 months or more of essentially zero vitamin D production. The summer window during which the sun is high enough for meaningful UVB penetration shrinks to just a few months, and even during that window, the intensity is low. Now put dark skin into this equation. Dark skin, remember, evolved to block UV radiation. That was its entire purpose, its reason for existing. In equatorial Africa, where UV levels are extremely high, blocking 90% of incoming radiation still leaves more than enough for vitamin D synthesis. The math works out perfectly. But at 55 degrees north, where UV levels are already perhaps 1/10 of equatorial values, dark skin blocking 90% of that already diminished radiation leaves only about 1% of the equatorial UV level reaching the vitamin D producing cells. 1%. And during winter, even that 1% drops to effectively zero. The result is chronic, severe, unrelenting vitamin D deficiency. Not a mild shortfall, not a temporary dip, a sustained, year-round deficit that the body cannot correct no matter what the individual does, because the fundamental physics of sunlight at high latitudes make it impossible for heavily pigmented skin to produce adequate vitamin D. And the consequences of that deficiency were devastating beyond anything you might imagine from hearing the term vitamin deficiency, which sounds mild and manageable and like something you could fix with a supplement. There were no supplements. There were no fortified foods. There was only the sun, and the sun was not strong enough, and dark skin was blocking what little there was. Let us walk through exactly what vitamin D deficiency does to a human body, because the details matter. They are not abstract biochemistry. They are the lived reality of your ancestors, the suffering they endured, the children they lost, the crisis that ultimately reshaped their bodies. The most immediate and visible effect is on the skeleton. Vitamin D is essential for calcium absorption in the intestines. Without adequate vitamin D, it does not matter how much calcium-rich food you eat. Your body simply cannot extract it from your digestive tract and move it into your bloodstream. And without calcium in the bloodstream, Your bones cannot mineralize properly. In children, the result is rickets. The name sounds almost quaint, like some old-fashioned ailment from a Dickens novel, but the reality is horrifying. Rickets means that the growing bones of a child do not harden as they should. They remain soft, pliable, deformable. As the child grows, as their increasing weight presses down on bones that cannot support it, the skeleton begins to warp. The legs are usually the first and most obvious casualty. The long bones of the thighs and shins, which bear the full weight of the body, bow outward or inward, creating the characteristic knock-kneed or bow-legged deformity that is the hallmark of the disease. But it does not stop there. The ribs develop abnormal bumps at the points where cartilage meets bone, creating a pattern called the rachitic rosary that can be felt through the skin as a series of hard knobs running down both sides of the chest. The skull softens, becoming vulnerable to deformation. The spine curves and compresses. The wrists and ankles thicken with abnormal bone deposits. The entire skeleton becomes a distorted, weakened version of what it should be. A child with rickets is not just physically deformed. They are fundamentally compromised. Their weakened bones fracture easily. Their misshapen ribcage cannot expand properly, reducing lung capacity and making respiratory infections more dangerous. Their deformed spine may compress the spinal cord, causing pain and neurological problems. They are shorter than they should be, weaker than they should be, more vulnerable to every physical challenge that life in a prehistoric environment throws at them. In adults, the equivalent condition is called osteomalacia. Your existing bones, the ones that mineralized during your childhood and adolescence, begin losing their mineral content. They become progressively softer and weaker, not because they are being actively damaged, but because your body, desperate for calcium it cannot absorb from food, begins pulling it from the only reservoir available, your skeleton. Your bones literally dissolve from the inside, losing density and strength in a slow, relentless process that leaves them increasingly fragile. The symptoms are miserable: chronic, diffuse bone pain, especially in the hips, lower back, and legs. Muscle weakness that makes it difficult to walk, climb, carry loads. All the activities that survival in a prehistoric environment required. Fractures from minor impacts that a healthy skeleton would shrug off. Imagine being a hunter who needs to chase game across broken terrain, or a mother who needs to carry a child and a load of gathered food back to camp, and your bones ache with every step and might snap if you stumble. But the skeletal effects, as terrible as they are, were not the worst of it. Vitamin D does far more than regulate calcium. It is deeply embedded in the immune system, playing a critical role in the activation and regulation of immune cells. Without adequate vitamin D, the body's ability to fight infections plummets. Specific immune cells called T cells require vitamin D to activate. When they encounter a pathogen, a virus or bacterium, they check for vitamin D before mounting a response. If vitamin D levels are too low, the T cells remain inactive. They detect the threat but cannot respond to it. The infection proceeds unchecked, or at least inadequately checked, leading to more severe illness, longer recovery times, and higher mortality rates. In the disease-rich environments of prehistoric Europe and Asia, where humans were encountering new pathogens with every new territory they entered, this immunological weakness would have been devastating. Respiratory infections that a healthy immune system could contain and clear would instead become severe, potentially fatal illnesses. Wound infections that should have been minor would fester and spread. Gastrointestinal parasites that a robust immune response could suppress would multiply unchecked, further draining the body's resources. Think about what this means for a small, isolated group trying to survive in Ice Age Europe. Every member of the group is essential. Every hunter matters. Every gatherer matters. Every mother matters. When a significant portion of the group is chronically ill, chronically weakened, chronically unable to perform at full capacity because their immune systems are running on fumes, the entire group's survival is compromised. Hunting success declines. Food stores shrink. Vulnerable members, the very young and the very old, die at higher rates. The group contracts, loses genetic diversity, loses knowledge, loses the critical mass of healthy adults it needs to sustain itself. Vitamin D deficiency also disrupts neurotransmitter production in the brain. Serotonin, The chemical messenger associated with mood regulation requires vitamin D for its synthesis. Chronic deficiency leads to depression, lethargy, cognitive impairment, and difficulty concentrating. In modern populations, the correlation between low vitamin D levels and depression is well established. Imagine the effect on prehistoric populations. People who needed to be alert, motivated, and cognitively sharp to survive in a dangerous environment were instead battling the foggy, energy-sapping effects of serotonin depletion. Their ability to plan, to solve problems, to respond quickly to threats, all diminished by a biochemical deficit they could neither understand nor correct. The hormone also plays a role in regulating cell growth and proliferation. People with chronic vitamin D deficiency show increased rates of various cancers. Their cardiovascular systems do not function optimally. Their muscles do not contract as efficiently because calcium, which is also essential for muscle function, is not being properly absorbed. Everything is connected. Everything is affected. The entire body runs less efficiently, less effectively, less reliably. But the single worst effect of vitamin D deficiency, the one that turned a serious health problem into an existential evolutionary crisis, was what it did to reproduction. Specifically, what it did to women's ability to survive childbirth. I need you to picture this clearly, because it is the heart of the story. It is the reason your skin looks the way it does. It is the engine that drove the most dramatic change in human appearance since our ancestors lost their body hair and stood upright millions of years ago. Imagine a young woman living in what is now Central Europe. It is perhaps 40,000 years ago. She has survived childhood, which in this time and place is already a remarkable achievement. She has grown up in a small band of hunters and gatherers, learning to track game through forests of pine and birch, to identify edible roots and berries in landscapes that are buried under snow for half the year, to prepare animal hides for warmth, to maintain fires through long dark winters. She has found a mate. She is pregnant with her first child. By the standards of her time and place, everything looks promising. Her group has food stored for the winter. The rock shelter where they are living is secure and well protected from the wind. She is young, strong, experienced in the skills she needs to survive. She has every reason to expect that she will deliver a healthy baby and raise it to adulthood. But there is something wrong with her that she cannot see and cannot know. She grew up at a latitude where the winter sun hangs so low that it might as well not exist. Her dark skin, inherited from countless generations of African ancestors, blocked the vast majority of the weak UVB radiation that reached her during the brief northern summers. Year after year, from infancy through adolescence, her body could not produce enough vitamin D. Year after year, her bones did not mineralize as fully as they should have. The effects were subtle. Maybe she was slightly shorter than she would have been with adequate vitamin D. Maybe she got sick a little more often than the healthiest members of her group. Maybe she felt tired more frequently, or her back ached more than it should have for someone her age. But she survived. She adapted. She compensated. She was tough and resourceful, as all her people were, and she pushed through the discomfort without ever understanding its cause. But her pelvis tells a different story. The pelvis is the most structurally critical part of the human skeleton when it comes to childbirth. It is the bony ring through which the baby must pass during delivery. Its shape, its dimensions, the angles of its various components, all of these must fall within a relatively narrow range for a safe vaginal delivery to be possible. And the pelvis, like every other bone in the body, requires adequate vitamin D during development to mineralize properly and achieve its correct shape. Rickets deforms the pelvis. Even mild rickets, the kind that might not produce obviously bowed legs or a visibly deformed ribcage, can alter the pelvic dimensions just enough to matter. The inlet might be slightly too narrow. The outlet might be angled incorrectly. The sacrum might be positioned a few degrees off from where it should be. None of these changes would be visible from the outside. The woman would look perfectly healthy, perfectly normal, perfectly capable of bearing children, until she goes into labor, and then the baby cannot pass through. The head, which in human infants is already nearly at the maximum size that can fit through a normal pelvis, encounters resistance. The bones are in the wrong position. The canal is too tight. Labor stalls. Contractions continue, growing stronger and more frequent, but the baby does not descend. In the modern world, this is a stressful but manageable situation. An obstetrician recognizes the problem, and a cesarean section is performed. Mother and baby both survive, typically without serious complications. In prehistoric Europe, there was no cesarean section. There was no obstetrician. There was no intervention of any kind that could solve this problem. When a baby could not fit through the birth canal, the outcome was almost always the same. Both mother and child died. Sometimes quickly, sometimes over the course of agonizing hours or days. But the result was the same. 2 lives lost. A woman who had survived everything else that this harsh environment had thrown at her, killed by the shape of her own skeleton. A child who never took a first breath. This was not a rare occurrence. This was not an occasional tragedy that struck an unlucky few. Archaeological evidence from early northern populations shows widespread pelvic deformities consistent with developmental vitamin D deficiency. Skeletal remains from these populations display the telltale markers: subtle but significant alterations in pelvic geometry, bowed long bones, rachitic changes in ribs and skull. These were populations in which a substantial fraction of women would have had compromised pelvises. Not all of them would have died in childbirth. Some would have been lucky, carrying smaller babies or having just enough pelvic clearance. But the death rate would have been significantly elevated compared to populations with adequate vitamin D status. And here is what makes this so particularly brutal. The women who died this way were the healthy ones. They were the ones who had been strong enough and lucky enough to survive childhood. The ones who had made it through the gauntlet of infectious diseases, injuries, malnutrition, and predators that killed so many children before they reached adulthood. They were the ones who had found mates, conceived successfully, and carried pregnancies to term. They had done everything right. They had beaten every other odd. And then their own skeletons, shaped by years of invisible vitamin D starvation, killed them at the very moment they were trying to bring new life into the world. The mathematics of this were devastating for populations trying to establish themselves in northern latitudes. If even 10 or 15% of women in each generation died in childbirth due to pelvic deformities caused by vitamin D deficiency, the demographic consequences were severe. But the losses did not stop there. Women who survived childbirth but had chronic vitamin D deficiency would have had weaker immune systems, higher rates of illness, longer recovery times, reduced breast milk quality, and compromised ability to care for their infants. Their babies, also vitamin D deficient from birth, would have had higher mortality rates in infancy and childhood. Fewer children born, fewer surviving, fewer reaching adulthood, fewer reproducing. Run this calculation forward over 100 generations, 500 generations, 1,000 generations, and the conclusion is inescapable. Dark-skinned populations in northern latitudes could not sustain themselves indefinitely. The vitamin D crisis was not just making life harder. It was slowly, relentlessly pushing these populations toward extinction. Without a solution, dark-skinned humans in Europe and northern Asia would have eventually disappeared, swallowed by the mathematics of insufficient reproduction. And yet they did not disappear. Obviously, they did not disappear, because you may well be sitting here right now with pale skin that tells the story of how your ancestors solved this problem. But that solution was not planned. It was not designed. It was not the product of anyone's conscious effort or deliberate choice. It was an accident. A series of accidents, actually. Random errors in the copying of DNA that happened to produce, in a few fortunate individuals, skin that was slightly less pigmented than the norm. Skin that let a little more of the scarce northern UVB radiation through. Skin that could synthesize just a little more vitamin D. Those individuals were healthier. Their bones were stronger. Their immune systems functioned better. If they were women, their pelvises developed more normally, and they could deliver babies safely. If they were men, they were more vigorous, more resistant to illness, better hunters, more attractive mates. They had more children who survived to adulthood, and those children inherited the genetic mutations that made their parents' lighter skin possible. Natural selection had found its lever, and it was about to pull it with extraordinary force. Now we arrive at the molecular heart of the story, the place where evolutionary pressure meets random chance and rewrites the appearance of entire populations. This is where it gets precise, where we can name the specific genes, identify the specific mutations, and trace their spread through human populations with a level of detail that would have been unimaginable just a few decades ago. Your ancestors are living in Northern Europe and Northern Asia. They have been there for thousands of years, long enough for the vitamin D crisis to become a permanent feature of their existence. Women are dying in childbirth. Children are growing up with soft, deformed bones. Immune systems are failing. The population is under siege from an enemy it cannot see and does not understand. Natural selection is screaming for a solution. Every generation, the individuals with the most melanin, the darkest skin, are slightly less likely to reproduce successfully. Every generation, the individuals with slightly less melanin, slightly lighter skin, are slightly more likely to survive and pass on their genes. The pressure is enormous, constant, unrelenting. But evolution does not plan. It does not design solutions. It does not sit down and think about what would help and then create it. Evolution is blind. It works by waiting for random changes in DNA and then letting the environment decide which changes are beneficial and which are not. Most mutations are neutral, doing nothing noticeable. Many are harmful, reducing fitness and being eliminated. But occasionally, very rarely, a mutation arises that happens to solve a problem the environment is posing. And when that happens, natural selection seizes upon it and spreads it through the population with breathtaking speed. In some individual whose name will never be known, whose face we will never see, whose life we can only dimly imagine, a copying error occurred during the replication of their DNA. Somewhere in the 3 billion base pairs that make up the human genome, a single nucleotide was substituted for another. One letter in an encyclopedia of genetic instructions was changed, the molecular equivalent of a typo. This particular typo occurred in a gene called SLC24A5, which sits on chromosome 15. SLC24A5 encodes a protein that plays a role in melanin production within melanocytes, the specialized cells in the skin that manufacture pigment. The protein functions as a cation exchanger in the membranes of melanosomes, the organelles within melanocytes where melanin is actually synthesized. The specific mutation was a change at position 111 in the protein sequence, where an amino acid called alanine was replaced by an amino acid called threonine. One amino acid, out of the hundreds that make up this protein. One change in one protein out of the tens of thousands of proteins that the human genome encodes. And that one change reduced melanin production by an estimated 30 to 40%. The person born with this mutation would have been visibly different from everyone around them. Not white, not pale in the way we think of modern Northern Europeans, but noticeably lighter than their parents and their peers. In a population where everyone was dark brown or very dark brown, this individual would have stood out. Their skin would have had a distinctly lighter tone, something between the deep brown of their relatives and the medium brown that we might associate today with populations living closer to the tropics. In most times and most places in human history, this mutation would have been insignificant, perhaps a mild disadvantage. Actually, since lighter skin is more vulnerable to UV damage and folate depletion in high UV environments. The individual might have passed the mutation to a few children, and those children might have passed it to a few of their children, but without any particular survival advantage. The mutation would have drifted through the population randomly, neither increasing nor decreasing in frequency, and eventually it would have disappeared entirely, a footnote in the genetic record that nobody would ever notice. But that is not what happened. Because this mutation did not arise in equatorial Africa. It arose in the north, in a place where UVB radiation was scarce and where dark skin was a liability. In a population that was being slowly ground down by vitamin D deficiency and all its devastating consequences. And in that specific context, at that specific latitude, under those specific conditions, this one tiny molecular change was the difference between life and death. The individual with the SLC24A5 mutation could synthesize vitamin D more efficiently than anyone around them. Their lighter skin let more UVB photons through to the vitamin D-producing cells in the deeper layers of the epidermis. Not a lot more, maybe 30% more. But in an environment where everyone was operating at the razor edge of deficiency, 30% more was enormous. It was the difference between bones that mineralized properly and bones that did not. The difference between a pelvis that could deliver a baby and a pelvis that could not. The difference between an immune system that could fight off a winter respiratory infection and one that could not. If the person carrying this mutation was a woman, she was more likely to survive childbirth. She was more likely to carry multiple pregnancies successfully. She was more likely to produce healthy children with properly formed skeletons and functional immune systems. She was more likely to live long enough to raise those children to independence and perhaps even help raise her grandchildren. If the person was a man, he was more vigorous and more resistant to disease. He was a better hunter, a more reliable provider, a more attractive mate. He fathered more children, and more of those children survived. Either way, the outcome was the same. The mutation spread, not because anyone decided it was good, not because lighter skin was considered more attractive, not because of any conscious choice or cultural preference. It spread for the simplest and most powerful reason in all of biology, because the people who carried it had more surviving offspring than the people who did not. This is natural selection in its purest, most elemental form. A random genetic change, an environmental pressure, a survival advantage, and the slow, inexorable mathematics of differential reproduction doing what it always does, amplifying beneficial traits and diminishing harmful ones, generation after generation, until the entire population has been transformed. Within a few dozen generations, perhaps 1,000 years, perhaps less, the SLC24A5 mutation had become common in the population where it arose. Within a few hundred generations, it had become dominant, and eventually, it became nearly universal, carried by virtually every individual in the population. The speed of this change tells us something about the intensity of the selection pressure. In population genetics, the rate at which a new mutation spreads is directly proportional to the survival advantage it confers. A mutation that provides a 1% advantage might take tens of thousands of years to reach fixation. The SLC24A5 mutation spread so quickly that it must have provided an advantage of several percent or more, possibly much more. In evolutionary terms, that is a massive selective advantage, comparable to antibiotic resistance in bacteria or pesticide resistance in insects. But SLC24A5 was not working alone. It was just the first instrument in an orchestra of genetic changes that were about to transform the appearance of northern populations. Around the same time, or perhaps a few thousand years later in a different population or even the same one, another random mutation appeared in another gene. This gene, called SLC45A2, also sits on chromosome 5 and also encodes a protein involved in melanin synthesis within melanosomes. The mutation in SLC45A2 further reduced melanin production through a slightly different mechanism, affecting the transport of precursor molecules needed for melanin assembly. An individual carrying both the SLC24A5 mutation and the SLC45A2 mutation would have been lighter still, not twice as light, because the genetics of pigmentation are not simply additive, but noticeably paler than someone carrying only one of the two mutations. And in the vitamin D scarce environment of northern latitudes, that extra lightness provided an extra survival advantage. More UVB penetration, more vitamin D synthesis, stronger bones, healthier pregnancies, better immune function. Then came mutations in other genes. TYRP1, which affects the type of melanin produced, shifting the balance from the darker eumelanin toward the lighter pheomelanin. OCA2, a gene on chromosome 15 that influences melanin production through yet another pathway, and that also, as a side effect, affects eye color. This is why skin color and eye color often change together in populations. They are influenced by overlapping sets of genes. The same mutations that lighten skin in European populations also produce the blue and green eye colors that are characteristic of those populations. MC1R, the melanocortin-1 receptor gene, underwent multiple independent mutations in northern populations. This gene encodes a receptor on the surface of melanocytes that, when activated, stimulates the production of eumelanin, the darker form of melanin. Mutations that reduce the function of MC1R shift melanin production toward pheomelanin, the reddish-yellow form, resulting in lighter skin and, in some cases, red hair and freckles. The prevalence of red hair in populations of northern European descent, particularly in Scotland, Ireland, and Scandinavia, is a direct consequence of MC1R variants that arose and spread under the selective pressure of the vitamin D crisis. Each of these mutations, taken individually, had a relatively modest effect on skin color. But together, carried in combination by individuals who inherited multiple lightning mutations from both parents. They were transformative. A person carrying the derived variants of SLC24A5, SLC45A2, TYRP1, OCA2, and MC1 are simultaneously would have had skin dramatically lighter than their ancestors of just a few thousand years earlier. Light enough to look, to our modern eyes, recognizably European. Pale, pink-toned, freckled, perhaps, blue-eyed, red-haired, or blonde. An appearance that seems timeless and ancient, but was in fact startlingly new. And here is something that adds another remarkable layer to this story. These mutations did not all happen in the same place. They did not spread from a single source. The genetic evidence shows us that different populations, facing the same environmental pressure of reduced UVB radiation at high latitudes, evolved lighter skin through completely different genetic pathways. The SLC24A5 mutation that is nearly universal in modern Europeans is almost completely absent in East Asian populations. If you are of Chinese or Japanese or Korean ancestry, you almost certainly do not carry it. But East Asians also have relatively light skin. They achieved it through different mutations in different genes, particularly through variants in OCA2 and in other pigmentation genes that scientists are still in the process of identifying and characterizing. This is a phenomenon that biologists call convergent evolution. Two separate populations, living in similar environments on opposite sides of the world, facing the same survival challenge, independently evolving the same solution through entirely different molecular mechanisms. It is like two engineers in different countries, speaking different languages, using different tools, independently designing a bridge that looks almost identical from the outside, but is constructed completely differently on the inside. Convergent evolution tells us something profound about the relationship between environment and biology. It tells us that the lightening of skin in northern populations was not a unique historical event that happened once and then spread. It was an inevitable consequence of the physics of UVB radiation and the biology of vitamin D synthesis. Any population of dark-skinned humans that settled at high latitudes for long enough would have faced the same crisis and evolved the same general solution, even if the specific genetic details differed. The environment did not care which genes changed. It only cared about the result, lighter skin that could produce more vitamin D. This has happened at least twice, independently, in European and East Asian populations. It may have happened additional times in other groups that we have not yet fully studied. The more we learn about the genetics of skin color in diverse human populations, the more examples of convergent evolution we find. The same problem, solved the same way, through different molecular pathways, again and again and again. Now let us talk about timing, because this is where the story takes a turn that genuinely surprises most people, including many scientists when the evidence first emerged. These mutations are recent. Not just recent in the grand sweep of evolutionary history, where anything less than 1 million years counts as new. Recent in terms that are meaningful on a human scale. Recent enough to overlap with events that we think of as belonging to recorded history or close to it. The SLC24A5 mutation shows genetic signatures of intense positive selection beginning somewhere between 10,000 and 20,000 years ago. Some analyses push the date even more recently, suggesting that the mutation may not have begun its dramatic spread through European populations until 8,000 or even 6,000 years ago. Think about what that means. 6,000 years ago, the pyramids of Egypt were about to be built. The first cities in Mesopotamia were already ancient. Writing had been invented. Agriculture had been practiced for thousands of years. Civilizations existed. And the people living in Northern Europe still did not have pale skin. We have direct physical evidence for this. The oldest complete genome recovered from a European individual comes from a man who lived in what is now Spain approximately 7,000 years ago. His remains were found in a cave called La Brana, and when scientists sequenced his DNA, they discovered something that would have seemed impossible just a generation earlier. He had dark skin, not medium brown, not olive, not tan. Dark skin, similar in shade to modern sub-Saharan African populations. He also had blue eyes, which had evolved earlier through mutations in a different set of genes. Dark skin and blue eyes. A combination that seems jarring and impossible to modern sensibilities, but was apparently perfectly normal in ancient Europe. He was not unusual. Other ancient European genomes from similar time periods tell the same story. The Mesolithic hunter-gatherers who inhabited Europe before the arrival of farming populations from the Middle East were, by and large, dark-skinned. They had lived in Europe for tens of thousands of years, and while they had likely become somewhat lighter than their original African ancestors, they had not yet undergone the dramatic lightening that characterizes modern European populations. The pale skin we associate with Northern Europeans today is, in evolutionary terms, brand new. It is newer than pottery, newer than the domestication of most animals, newer than the oldest surviving works of art and architecture. In the roughly 300,000-year history of modern humans, pale European skin has existed for perhaps the most recent 2 or 3% of that time. For the other 97%, the people living in Europe were dark. This challenges everything most people assume about the relationship between geography and appearance. We tend to imagine that Europeans have always been pale, that the association between northern latitude and light skin is ancient and primordial. It is not. It is very, very recent. And the speed at which it occurred tells us just how powerful the evolutionary pressure must have been. To go from dark skin to pale skin in 6 to 10,000 years, which is perhaps 200 to 400 human generations, requires a selection pressure that is extraordinarily strong. Population geneticists have calculated that the survival advantage conferred by the SLC24A5 mutation alone must have been on the order of 5 to 10%, meaning that individuals carrying the mutation were 5 to 10% more likely to survive and reproduce than those without it. In the normally glacial pace of human evolution, that is an enormous advantage, comparable to the most powerful selective forces ever measured in any species. 5 to 10% might not sound like much in everyday terms, but compounded over 200 generations and the effect is staggering. It is like compound interest on a savings account. A small percentage advantage, applied consistently over many generations, produces enormous changes. Within just a few thousand years, a mutation that initially appeared in a single individual can become universal in a population of millions. And that is exactly what happened. The lightning mutations did not gradually drift through European and Asian populations over tens of thousands of years. They swept through with a speed that left clear signatures in the genome, signatures that population geneticists can detect and measure. These signatures, called selective sweeps, occur when a strongly favored mutation increases in frequency so rapidly that it drags along neighboring sections of DNA, creating telltale patterns of reduced genetic variation in the chromosomal region surrounding the selected gene. The selective sweeps around SLC24A5 and SLC45A2 in European populations are among the strongest ever detected in the human genome. Whatever was driving the spread of these mutations, it was pushing harder and faster than almost any other selective force in human evolutionary history. But here is what really matters. What you should carry with you as this story continues to unfold. These dramatic changes, these transformations that altered the appearance of entire continental populations, involved a tiny, almost absurdly small fraction of the human genome. Current research suggests that the vast majority of visible skin color variation among modern humans is controlled by somewhere between 15 and 30 genes. Probably fewer than 20 account for the differences that most people would notice. 20 genes, out of approximately 20,000 protein coding genes in the human genome. That is 0.1% of your genetic code. A person with very dark skin and a person with very pale skin, standing side by side, looking as different as two humans can possibly look, are genetically identical at 99.9% of their genome. The difference that seems so vast, so fundamental, so significant that entire civilizations have been built around it, wars have been fought over it, systems of oppression have been justified by it, is the result of minor variations in a microscopic sliver of DNA. These variations affect melanin production in the skin. That is it. That is all they do. They do not affect the brain. They do not affect intelligence or personality or temperament or moral character or athletic ability or artistic talent or anything else that actually defines a human being as an individual. They could not possibly affect those things. Because cognitive and behavioral traits are controlled by thousands of genes working in enormously complex networks that have nothing to do with the handful of genes that determine how much pigment your melanocytes produce. The mutations that change skin color. Nothing more. They were a simple biochemical adjustment to a single physiological system, made necessary by changes in UV radiation exposure as populations moved to different latitudes. An evolutionary adaptation as straightforward and as biologically trivial as the development of thicker fur in Arctic mammals or the change from dark to light plumage in birds that live in snowy environments. And yet humans, with our extraordinary capacity for pattern recognition and our equally extraordinary capacity for drawing incorrect conclusions from observed patterns, looked at these superficial variations and decided they must mean something profound. We constructed categories. We invented hierarchies. We built elaborate mythologies to explain differences that were actually nothing more than adaptations to different amounts of sunlight. We turned a minor biochemical adjustment into something we imagined was deep and fundamental and meaningful, and we used that imagined meaning to justify centuries of cruelty. The genetics says otherwise. The genetics says these changes were recent, superficial, and convergent. It says skin color is among the least important ways that humans differ from one another. It says we have been fighting for thousands of years over something that matters, genetically speaking, about as much as whether your earlobes are attached or detached. But the evolutionary story was not finished. The mutations had appeared. They were spreading. Natural selection was doing its relentless work, favoring lighter skin in populations where vitamin D deficiency was a life or death problem. Given enough time, the mutations would have spread to fixation on their own, reaching near universality in northern populations over perhaps 10 to 20,000 years. But something was about to happen that would accelerate this process dramatically. Something that would take the already powerful selective pressure for lighter skin and amplify it tenfold. Something that would compress what might have been 20,000 years of gradual change into perhaps 5,000 years of rapid transformation. That something was not a natural event. It was not a climate shift or a new migration or a volcanic eruption. It was something that humans did to themselves, something they invented, something that seemed at the time like the greatest advance in the history of their species. It was farming, and it was about to change everything, including, in ways that no one could have predicted or intended, the color of human skin. The agricultural revolution was coming, and it carried within it consequences that would ripple through human biology in ways that are still being discovered and understood today. The crops that would feed civilizations would also starve bodies of a critical nutrient. The settled lifestyle that would build cities would also trap populations in conditions that demanded lighter skin or death. The dietary shift that would transform human culture would also transform human appearance, pushing evolution into overdrive and producing, in just a few thousand years, the pale-skinned populations that we think of today as having existed since time immemorial. They had not. They were brand new. And the story of how they got that way was about to enter its most dramatic and fastest-moving chapter. The agricultural revolution. We talk about it like it was humanity's greatest triumph. And in many ways it was. Cities, writing, mathematics, science, law, everything we call civilization traces back to the moment when humans stopped wandering and started planting seeds. Without agriculture, none of it exists. But here is what the triumphant version leaves out. For the people who actually lived through the transition, farming was a disaster. A slow-motion catastrophe that degraded human health in ways that are still visible in the archaeological record thousands of years later. And buried within that catastrophe was an unintended accelerant that would supercharge the evolution of pale skin and compress what should have taken tens of thousands of years into just a few millennia. To understand why, you need to understand what hunter-gatherers actually ate. The popular image of prehistoric people as desperate, half-starved scavengers is almost completely wrong. Hunter-gatherers ate extraordinarily well, not luxuriously, but nutritionally. A typical group in Northern Europe might consume dozens of different foods in a single week. Wild game for protein and fat, fish and shellfish for omega-3s, and, crucially, vitamin D. Wild roots, berries, nuts, fungi, leafy greens for vitamins and minerals. The diversity was remarkable, and it was the key to their nutritional success. Most importantly for our story, hunter-gatherers in northern latitudes had reliable dietary sources of vitamin D. Fatty fish like salmon, mackerel, and herring are packed with it. A single serving of wild salmon contains more vitamin D than most modern people get in an entire day. Animal liver, which hunter-gatherers prized and ate preferentially, often giving it to pregnant women and growing children, is another rich source. Seal meat and seal fat, for coastal and Arctic populations, contain massive amounts. This is why populations like the Inuit were able to thrive at extreme northern latitudes without ever developing pale skin. Their traditional diet, based almost entirely on marine mammals and fish, provided so much dietary vitamin D that their dark skin was never a significant liability. They solved the vitamin D problem through food rather than through genetic change. Without selective pressure to lighten, their skin stayed dark. The Inuit are living proof that skin color evolution was driven not just by latitude and sunlight, but by the interaction between sunlight and diet. For other northern hunter-gatherer populations, the dietary vitamin D from fish and game was helpful, but not always sufficient. During long, dark winters when fresh fish was scarce and stored meat was the primary food, vitamin D reserves would drop. Darker-skinned individuals suffered more from these seasonal deficits, and lighter-skinned individuals had a modest advantage. The selection pressure for lighter skin was real, but it was partially buffered by dietary sources. Evolution was moving, but not at emergency speed. Then came farming, and the buffer vanished. Agriculture emerged independently in several locations between roughly 12,000 and 8,000 years ago. In the Fertile Crescent, people domesticated wheat and barley. In China, rice and millet. In Mesoamerica, maize and beans. In each case, a few wild plant species were selectively cultivated until they became the foundation of the entire food supply. The advantages were immediate. More calories per acre, larger populations, food surpluses, permanent settlements, specialization and trade. The foundations of everything we call civilization. But the nutritional cost was staggering. Where a hunter-gatherer might eat 50 or 100 different foods over the course of a year, an early farmer might depend on 3 or 4 crops for the vast majority of their calories. Wheat, barley, maybe some lentils. And that was essentially it. This monotonous diet was deficient in almost everything except raw calories. The archaeological evidence is unambiguous. Early farming populations were shorter than their hunter-gatherer predecessors, sometimes by 4 to 6 inches. Their teeth were riddled with cavities from starchy carbohydrates. Their bones showed signs of mineral deficiency. They suffered from infectious diseases that had been rare in mobile hunter-gatherer groups, diseases that jumped from domestic animals to humans in the crowded conditions of farming villages. And they were catastrophically vitamin D deficient. Because here is the critical fact. Grains contain essentially no vitamin D. Neither do most vegetables, fruits, or legumes. Plants simply do not produce this molecule. When you base your entire diet on cultivated grains, you cut yourself off from dietary vitamin D almost completely. Early farmers did keep some domestic animals, but the meat they consumed was a smaller proportion of their total diet than it had been for hunter-gatherers, and they typically ate muscle meat rather than the vitamin D-rich organ meats that their ancestors had prized. Grain was cheaper, easier to store, more reliable. It became the foundation of every meal, with animal products reduced to an occasional supplement. The result was a population almost entirely dependent on sunlight for vitamin D, with virtually no dietary backup. And in northern latitudes, where sunlight was already insufficient for dark-skinned individuals, the elimination of dietary sources transformed a chronic problem into an acute crisis. Imagine the scenario clearly. You are a farmer in what is now Denmark, 7,000 years ago. Your diet is bread and porridge and whatever vegetables you can grow in the short northern summer. Winter arrives. The sun barely clears the horizon. For 5 or 6 months, your body produces 0 vitamin D. In the old days, your hunter-gatherer ancestors would have compensated with fish and animal liver. But you live inland now, tied to your fields. Your diet is grain. Your belly is full, but your body is starving for a nutrient that simply is not there. Your bones soften. Your muscles weaken. Your immune system fails. Your children grow up stunted and deformed. Your daughters, when they reach childbearing age, have pelvises shaped by years of vitamin D starvation and some of them die in labor. This was not hypothetical. The archaeological record confirms it in gruesome detail. Early farming populations in northern Europe showed dramatically elevated rates of rickets, osteomalacia, skeletal deformities, and infectious disease compared to the hunter-gatherers they replaced. The evolutionary pressure for lighter skin, which had been significant but partially buffered under hunter-gatherer conditions, suddenly became overwhelming. It was no longer a modest advantage. It was survival versus extinction. Women with lighter skin could produce enough vitamin D to develop normal pelvises and survive childbirth. Women with darker skin could not. Children with lighter skin could mineralize their bones and fight infections. Children with darker skin could not. The selection differential may have jumped from 5 or 10% to 20 or 30% or higher. And when natural selection pushes that hard, the results are dramatic and fast. This is why the genetic signatures of selection on skin color genes in European populations are among the most powerful ever detected in the human genome. This is why the selective sweeps around SLC24A5 and SLC45A2 are so extraordinarily strong. This is why pale skin appeared so recently and spread so fast. Agriculture did not create the pressure for lighter skin. That pressure had existed since humans first moved north. But agriculture amplified it to a degree that had never existed before. Within roughly 5,000 years, European populations went from dark or medium brown skin to the pale, pink, freckled appearance we associate with northern Europeans today. What might have taken 20 or 30,000 years under hunter-gatherer conditions happened in 5 or 6,000 under agricultural conditions. The farming revolution changed not just what humans ate and how they lived. It changed what they looked like. And this same process played out independently wherever agriculture replaced hunting and gathering at high latitudes. In northern China, where millet and rice-based diets were equally devoid of vitamin D, light skin evolved through different genetic mutations in response to exactly the same nutritional pressure. In Korea, in Japan, in Central Asia, the same pattern repeated. Different genes, same result. Convergent evolution driven by the same dietary catastrophe. Now let us step back and look at the full picture. The global map of human skin color, when you see it clearly, tells the entire story in a single image. Start at the equator. In equatorial Africa, South America, Southeast Asia, and the Pacific Islands, populations have dark skin. The ancestral condition, maintained by ongoing selection for UV protection in high radiation environments. Move north or south, and skin lightens. Gradually, smoothly, in a continuous gradient that tracks declining UV intensity. The Middle East, Southern Europe, Central Asia, Southern China all show intermediate tones. Olive, tan, golden brown. Continue to higher latitudes, and the lightening continues. Northern Europe, Northern China, Korea, Japan. The palest populations are those that have lived at the highest latitudes the longest and have been most dependent on grain-based diets. But the gradient has exceptions, and every exception proves the rule. The Inuit, dark at extreme latitudes because their marine diet eliminated the need for sun-based vitamin D. The Tibetans, relatively dark at high altitude because UV is intense at elevation. The Australian Aboriginals, dark at latitudes comparable to southern Europe because Australian UV is intense, and their traditional diet included adequate vitamin D. Every exception can be explained by the same principles. UV levels, dietary vitamin D, genetic history, time in the current environment. No mysteries, no anomalies, just biology doing what biology does. And the gradient is continuous. There are no boundaries, no dividing lines, no points where you can draw a border and say people on one side are one race and people on the other are another. Skin color changes as smoothly across geography as temperature changes from the equator to the poles. We took a continuous gradient and chopped it into arbitrary categories, and then pretended those categories were real and fundamental. They are not. They never were. The Human Genome Project and decades of subsequent research have confirmed this with absolute clarity. The total genetic variation in the entire human species is remarkably small. Two random humans differ at about 0.1% of their DNA. And of that tiny variation, 85 to 95% exists within populations, not between them. Two people from the same Nigerian village can be more genetically different from each other than either is from a randomly selected person in Finland. Skin color is controlled by perhaps 15 to 20 genes out of roughly 20,000. Less than 0.1% of the genome. A person with very dark skin and a person with very pale skin are genetically identical at 99.9% of their DNA. The visible difference that seems so vast and so significant is the result of minor tweaks to a microscopic fraction of the genetic code. Those tweaks affect melanin production. That is all they do. They do not affect the brain, intelligence, personality, temperament, capability, or any other trait that defines a human being. They cannot, because cognitive and behavioral traits are controlled by thousands of genes working in complex networks that have nothing to do with pigment production in skin cells. The idea that skin color reveals something fundamental about a person's nature is not just morally wrong. It is scientifically illiterate. It is a pre-scientific superstition that has been conclusively disproven by modern genetics. And yet, this superstition has shaped human history more profoundly than almost any other idea, used to justify slavery, colonialism, genocide, and countless other forms of cruelty in service of something that is simply, demonstrably false. The real story, the one told by DNA and fossils and biochemistry and physics, is not about division. It is about unity. One species, recently diverged from a common African ancestor, adapted to different environments through superficial modifications to a tiny shared genome. Differences that are real but shallow, recent but not fundamental, visible but not meaningful in any deep biological sense. So here we are, at the end of a journey spanning 300,000 years. From the sun-baked savannas where every human was dark, through the Great Migration out of Africa, through the vitamin D crisis of northern latitudes, through the random mutations that began lightening skin, through the agricultural revolution that accelerated the transformation beyond anything evolution normally allows. Look at your hand one more time. Whatever shade it is, you are looking at a story. A story written in melanin and ultraviolet radiation and vitamin D and the bones of women who lived and died tens of thousands of years ago. A story written by random mutations that happened to save populations from extinction. A story written by the farming revolution that changed human bodies in ways nobody intended. Every link in the chain held. Every generation found a way to survive and pass life forward. And now that story sits in your skin, a record of adaptation, resilience, and the extraordinary flexibility of the human body. We started in one place, looking one way. We scattered across the world, changed, diversified, transformed. And yet beneath the surface, beneath that thin layer of pigment, we remained exactly what we had always been. One species, one family, one unbroken line stretching back to the African sun and forward to wherever we are going next. That is the story written in your skin. And now you know how to read it.